Alright, so here we are, section 8.6. It's the last section of chapter 8. It's on exponential growth and decay. This is on page 357. So first thing to warm up, and of course if you have a calculator this is going to be super easy for you. You're just taking 2 to the 8th power, 2 to the 16th power, and 2 to the 24th power. Just a reminder real quick, I believe your exponent key looks something like this, x to the y power. So you would do 2, hit this key, and then hit the 8. That'd be 2 to the 8th power. That's going to give you 256. 2 to the 16th power is 65,536. And 2 to the 24th power is 16,777,216. So you can see how quickly these start to increase even with a base as small as 2. And then also for exponents with fractions, remember we're having to take this 8th applied to the 1 and to the 2nd. So it's 1 to the 8th power, which is 1, 2 to the 8th power, which is 1 over 256. And then same thing with the 16th power. So we have 1 to the 16th power is 1, and 2 to the 16th power is 65,536. So we are dealing with exponential growth. Exponential growth, or decay, occur when the value of a function has the same percent increase or decrease during each unit of time. So they have an example here. It says, under ideal conditions, the number of fish in a pond initially stocked with 1,000 fish increases by 50% each year. The next year's population is then 150% of the current population, because we have our current population, that's our 100%, and the 50% increase, that gives us our 150% of the current population. And then they give us a table there on page 357 that illustrates the exponential growth. And if you kind of picture it, of course they have a chart for you, but just think about it. If you started out with 100 and you were just increasing by 50%, that would only be 50 fish the next year. Whenever you have 1,000 fish and you're increasing by 50%, then you have 500 fish that year. So you can see it's going to be more of an increase each year. That's why it's an exponential growth. It's not just a plain linear equation. It's not a straight line. It's not consistent every year. It's becoming greater and greater each year. So similarly, exponential decay is whenever the value of a function has the same percent that decreases during each time. So in the fish example, it says, at some point the conditions necessary to sustain this growth cannot be maintained. So I don't know, maybe there's a parasite in the water, it starts killing our fish instead of them growing at 50% per year. So it says, suppose the population decreases by 25% each year after the population reaches 10,000. So maybe we just reached 10,000 and now there's not enough food to go around for all these fish, so they start dying off and we're losing 25% each year. That means next year our new population is only going to be 75% of what our current population is. And then there's also a table and a chart at the bottom there that you can check out on the bottom of page 357, which shows us that at the beginning it drops off very quickly, and then it starts to even out. And as there's less fish, there's less to drop off at the end of each year. So we have a definition. It says, given an amount A and the growth rate R, the exponential function f of t equals a times the quantity a plus r to the t power can be used to model both exponential growth and exponential decay. The quantity 1 plus r is called the growth factor. So that's a lot. If I were you, I would just write this in your notes and then label a few things. So first thing I would label is that they told us A is worth, or A is what? A is our initial amount. So A is the initial amount. Then it says 1 plus r is the growth factor. So we've covered our A, we've covered our 1 plus r. Now what is r? Well, r is our growth or decay rate. And then, of course, t would be our time. And the last thing it tells us about r is that r, well, let's say it this way. It's called exponential growth. This is the important part, that this is growth whenever r is greater than 0. And it's decay whenever r is greater than -1 and r is less than 0. So it's somewhere between -1 and 0 for decay. For growth, it is greater than 0. So example 1. It says for each exponential function, identify the initial amount, the growth rate, and the growth factor. Then state whether the function models exponential growth or exponential decay. So, for f of t equals 500 times the quantity 1 minus 0.75 to the t power. Well, our initial amount, remember that would be where our a was, so that's this here, would be 500. Our growth rate, that's r. Well, this is a negative 0.75. 0.75 is the same thing as 75%. And our growth factor would be 1 minus 0.75, or 100% minus 75%, which gives us 0.25. So, because we have a negative right here, and these are negative amounts, that means that this is decay, because r is less than 0. For 1b, if we take a look at just where everything's located in our formula, and you can refer back to your notes, the initial amount's 100, the growth rate is 2.5 or 250%. That makes the growth factor 3.5, and this is growth because we have a positive number in here. And r is greater than 0. That's telling us about our growth. How about for f of d equals 2d? Well, our initial amount is 1. It's kind of imaginary. We can't see it there. And we can actually rewrite it just like this. So we knew that this 2 had to be 1 plus r. So 1 plus what is going to be 2. That gives us a growth or rate of 1 or 100%. That makes our growth factor, which is given to us right here, is 2. And this is growth. What about this one? Well, our initial amount is given to us right here. It's 10,000. We know that our growth, this is our growth factor once it's all done. So we would have 1 plus something equals 1/2. So what would this something be? It'd be a negative 0.5 or a negative 50%. When we rewrite it, just like we just did up above there, gives us a growth factor of 1/2, which was given to us, and because it's a negative number here, and because this ends up being less than 1, we know this is decay. So example 2, in a single elimination tournament, half of the teams are eliminated in each round. Write an exponential function representing the number of teams left after each round in the tournament, beginning with 64 teams. So our initial amount is 64 teams. It's decaying, or they're being eliminated by half. Half of the teams are eliminated each time. And so we have our growth rate, or our decay rate in this case, it's a negative 1/2. Our initial amount's 64, and we just have our 1 minus and our decay. So that's our first part. B says determine the number of teams left after 3 rounds. Well, that means we just need to substitute in a 3 for our number of rounds. So we have f to the third, substitute out our n's for 3's. When we evaluate that, 64 times 1/2 to the third power, remember we have to do our order of operations, so we take 1/2 to the third power first, we get 64 times 1/8, and 64 times 1/8 equals 8 teams. So there are 8 teams left after 3 rounds. And then finally it says graph the function to find out how many rounds it takes to determine a champion. There's a graph on the bottom of page 358, and you can see from that that it takes 6 rounds to have 1 champion left. Example 3 says, a 5-gram mold culture increases in size by 200% every day. Write an exponential function modeling this growth to find the size of the culture after 1 week. So first of all, we need to write our function out here. We have said that the initial amount was 5. So we can find that right here, 5. Then it says it increases by 200% each day. So we have 200%, or that's 2. And notice they use D for day, so we remember that we're working in days, not weeks or months or years, but this is days. And then we can combine our like terms and just consolidate to make a kind of cleaner equation. And we end up with f to the d, or f of d equals 5 times 3 to the d power, because our 1 plus 2 was 3. And then it says, find the size of this culture after 1 week. Well, how many days are in 1 week? That'd be 7. So we take and evaluate for 7. F of 7 equals our 3 to the 7th power times 5. When we punch that in our calculator, we get 10,935 grams. Next up, we're going to take a look at some more compound interest. So at the bottom of your page 359, there is a chart for the compound interest formula. It says A equals P times the quantity 1 plus R to the X power, where A equals the account balance, P equals the principal amount, X equals the number of periods, and R equals the periodic interest rate. You might want to go ahead and throw those in your notes. And I would say probably if you have a note card, go ahead and put them on there too. So it says if there are n compounding periods in each of t years, then R equals APR over n. X equals NT, which I know is a lot. Once again, it's one of those that you just need to go ahead and use it. It'll make a little bit more sense. So example 4 on page 360. Mr. Mendoza invests $6,000 in a certificate of deposit, or a CD, earning 4% interest compounded quarterly. Write an exponential function modeling the value of his investment, write the account balance after 10 years, and create a table of order pairs and graph the function. So first of all, we know our initial amount is $6,000. Next up, we need to put in our quarterly interest rate. Well, we know our interest rate is 4%, and it's every quarter, so we have to divide that by 4. So 4% divided by 4 is 1%. And that's how we get our rates. Then we can plug that information into our formula. So we have 6,000 times our quantity of 1 plus our rate of 1% to the Q, where Q is the number of quarterly periods. So first off, that was our equation. Then it says, how about the balance the account after 10 years? Well, 10 years is 40 quarterly periods. 10 times 4 is 40. So we have to substitute 40 in for Q. When we solve, we get it's about $8,933.18. And then finally, we have example 5, which is on depreciation. So the value of many items decreases by the same percent each year. This is depreciation and can be modeled by an exponential decay function. So maybe you've heard that you shouldn't buy a new car because it depreciates so quickly, it's not worth it. It starts depreciating as soon as you drive it off the lot. So if you think of the graphs we've been seeing, it means that at the very beginning your car is depreciating really fast, and then eventually over the years it starts to kind of smooth out and not depreciate so quickly. Or maybe you've taken a video game or like your PlayStation or something into GameStop and tried to get money back for it, and you realize kind of the longer you wait, the less money you'll get in for it because it's not worth as much anymore. It's depreciated. So electronics, especially your computer, your car, your appliances around your house, all these things depreciate, and they are assigned a new value based on that depreciation. So the value of many items depreciates or decreases by the same percent each year, and that is depreciation. That's what we just talked about. So let's say example 5. There's an automobile that's sold for $30,000 depreciates at about $12,000 each year. Write an exponential function modeling the value of the car. Determine the value to the nearest $100 of the car after 5, 10, and 15 years, and find the loss of value of the car during its first 5 years, its second 5 years, and its third 5 years. So let's just take this one bit at a time. First thing, we know that our initial amount is $30,000 and that our growth rate is a negative 0.12 or a negative 12% because it is decreasing. So then when we take those values into our function, we get f of t equals 30,000 times the quantity of 1 minus our 12%, or 100% minus 12% to our t power. 1 minus 0.12 is 0.88, so we can go ahead and consolidate those. So that's our function that we're going to use here. And the first question said, well, what about after 5 years? So we can take 0.88 to the 5th power, multiply that by 30,000, and we'll get approximately $15,800. And that is the value of the car after 5 years. Then after 10 years, so we take 0.88 to the 10th power, multiply that by 30,000. We get that it's only worth $84,000 or $8,400, $8,400 after 10 years. And after 15 years, do the same thing, and we find out that it's worth $4,400. So you can see in the first 5 years it really dropped off really steep, and in the second 5 years, not quite so much. And then finally it says find the loss of value for the car during the first 5 years. Well, we went from 30,000 to 15,800, so we lost a value of $14,200 over the first 5 years. Label that, that's lost. It's loss of value, but I'm just going to say is lost after first 5. Then we went from 15,000 to 840, so it was a loss of value of 7,400 after the second 5 years. And then we went from 8,400 to 4,400, so we only lost $4,000 in the third set of 5 years. So you can see that's why a lot of people buy used cars, because they're getting more for their money essentially, and it's losing less value as the age of the car it gets older. So that's it for this last section in Chapter 8. Go ahead and check out your assignment and let me know if you have any questions.